Hi there, my name is Nathan Carlson. I'm a PhD candidate at the Canadian Institute for Theoretical Astrophysics and the University of Toronto. I'll be talking today about my work on looking for traces of primordial non-Gaussianity in the cosmic web with the WebSky simulations. So in this talk, I'll discuss how we look for signs of novel early universe physics in the cosmic web, the largest structures in the universe today. So I'll start with a bit of an intro on what non-Gaussianity is, why it's interesting, and how we can measure it. Then I'll talk about the tools I use to measure it, the Peak Patch-WebSky simulations, which we use to make mock cosmological observables. And then I'll talk about how we can actually use these observables to constrain inflation. Okay, so what is non-Gaussianity and how do we measure it? So as we all know, the cosmic microwave background is very nearly Gaussian. You bin up the data from the CMB, the cumulative distribution function looks like a normal distribution. But the thing is, inflation predicts that there should be some deviation from purely Gaussian statistics in these early universe distributions of energy. So if you can characterize that deviation from purely Gaussian statistics, what we call the non-Gaussianity, then you can actually probe the parameter space of possible inflation models. But the tricky thing is that other physics introduce non-Gaussianities. Nonlinear processes like gravitational collapse acting on a Gaussian field are going to give you a non-Gaussian field, at least a slightly non-Gaussian field. So yeah, I'll talk about kind of two questions we have in this talk. The first one is, how do we characterize that early universe non-Gaussianity? And the second is, how do we isolate that form of non-Gaussianity from these non-Gaussian foregrounds? So the first question about how we characterize it, typically we use this early universe scalar perturbation field called zeta, which couples to observable fields like the energy density of the universe. And this field has a very useful feature that it freezes out on superhorizon scales. So in this cartoon, I'm showing the time evolution of the zeta field in Fourier space. So as we know, inflation causes the horizon to drastically shrink, taking regions of space that were once causally connected and disconnecting them causally. And so in Fourier space, this is the opposite effect. You have the horizon scale growing. So K horizon grows over time, and as it does, the zeta modes at the corresponding scales exit the horizon and zeta stops evolving. And when zeta isn't evolving, it doesn't interact with these other fields. So what this means is you have this perimeter K horizon growing, and as inflation proceeds, as this grows, you're freezing out zeta at different scales. So this preserves information about what was going on during inflation. And then after inflation, once the real space horizon starts to grow again, these zeta modes are going to re-enter the horizon, and zeta will start evolving again, and it'll interact with observable fields. And so we can indirectly measure zeta, and in so doing, actually measure what was going on during inflation. So the way this is typically done is you assume zeta is mostly Gaussian with some small perturbative non-Gaussianity. And typically people look at single field inflation models. So you would expect to have a single underlying Gaussian field, which I've called zeta G. And then the non-Gaussian part of this field is just a nonlinear function of zeta G. So perturbation theory, lowest order, you have some constant called FNL times zeta G squared, and then you subtract out the variance. So FNL is like an amplitude, not really an amplitude, really you should pull out the variance, but whatever. So the point is, zeta is of order about 10 to the minus 5. So unless FNL is 10 to the 5, then this non-Gaussian piece is really small. And so there's this convenient thing where if you calculate the bispectrum using the right approximations, then this FNL comes out as a first order term in the bispectrum. So if you have a bispectrum estimator, you can measure FNL. We've done this, and FNL is small. It's consistent with 0, which means the non-Gaussianity of this form is really small. But the thing is, this is a correlated form of non-Gaussianity. Here I've shown a Gaussian field on the left and a correlated non-Gaussian field in the middle. So what this means is because the non-Gaussian part is constructed from the underlying Gaussian field, the peaks in the non-Gaussian part of the field overlap with peaks in the Gaussian part. And so this amplifies the non-Gaussian effect. But let's say we have a multi-field inflation model, which is really motivated by high energy physics. In high energy physics, we don't just have a single field that's important. There's a whole bunch of fields. So really, it makes more sense that you'd have a multi-field model, and other inflationary fields could become important at different times. So in this case, we've got a statistically very similar case. So we have an underlying zeta G field, and then we have a chi G field, which is statistically identical to zeta G. And it's made from the same power spectrum with different random number draw. And then we have another thing that I've called F and L tilde, just because I want to make sure it's clear it's not the same thing. And so in both cases, I've got F and L is 10 to the 5. But in the uncorrelated case on the right, we see this field looks a lot more like the Gaussian overdensity field. And the reason is because the peaks in the chi field are uncorrelated with the peaks in the zeta G field, so they don't overlap, and you bury the non-Gaussian effect. So if you can find some method that gives you uncorrelated non-Gaussianity, then it's much, much harder to measure it. It could be buried in the signal, and it's not going to come out in the bispectrum as easily. So one method that my colleagues are working on at CETA is primordial intermittent non-Gaussianity, or PNGs, if you like a cute little word for it. So this is a very general class of inflationary models where any multi-field inflation model that undergoes an instability, where you have this the left surface plot, or the right surface plot here shows you have a saddle point in the surface of inflationary potentials. So when this happens, you cause these pings to occur in the early universe fields, and this gives you a type of uncorrelated non-Gaussianity. So the resultant non-Gaussianity is you have your zeta field is equal to some underlying Gaussian part plus a functional of a second inflationary field, an uncorrelated chi G field. And so the effect is that you get this spike in the power spectrum. You're injecting power at a certain scale that's related to the model parameters for the instability, and then also just when the instability occurs during inflation. So this is, again, a very broad class of inflationary models. It's not just one niche model. Any multi-field inflation model that has a saddle point like this in the inflationary potential will give you this form of non-Gaussianity. And so it's wide open. It could happen at a range of different scales. And so it's a very interesting model to us because it can inject power at kind of any scale, basically. So I've done, again, kind of a cartoonish case here just to show, a huge spike in the power spectrum at where the power spectrum is highest. Obviously, this is ruled out. But just to show we've got kind of two different normalization schema. So one where the underlying Gaussian field is normalized to the Planck sigma 8 value, that would be this one. And then in this one, you have the total field is normalized to the same sigma 8 as Planck. So if you have the spike in the power spectrum, if it's very large, it doesn't have to be so large. But if it's very large and it's at the peak, then you're going to suppress the whole power spectrum. But if it's somewhere in the tails, it can get buried a lot more. Oh, and I should say this is work being done by my colleague Tom Morrison at CETA, another graduate student. He'll be publishing on this later this year. So stay tuned. Okay, so yeah, just wanted to quickly show the fields we're looking at. So you have this chi G field with some characteristic scale of structure that's going to correspond to that spike in the power spectrum. And the spike is going to happen at the same kind of characteristic scale. And you can see the same kind of scale, the same structures in chi G are appearing in delta zeta, which is the non-Gaussian part of the zeta field. And then that's, again, related to the overdensity field. So we can see how this tracks. Okay, so then how do I measure this non-Gaussianity? So I do this with a suite of simulations called Peak Patch and WebSky. So the Peak Patch simulations, you start with a power spectrum describing the energy density of the universe, and then we search this. We use this to make a realization of an initial energy density field, and then we search this field for the structures where dark matter halos will collapse. We run merging exclusion algorithms to make sure we're not double counting mass, and then we can displace these halos we find. And this gives us a catalog of dark matter halos. The major advantages of the Peak Patch simulations are that these halos can be run as, we can make light cone catalogs, which means you can put an observer at the center of your volume. And as you move out, halos are older and older. They're or younger and younger. They look like they're from the past, just like we see when we look out into the universe, which is something that's non-trivial to do with larger n-body simulations. And then it's also much more computationally efficient, and it particularly lends itself to just plugging in the power spectrum we need at that first step, which means we can easily incorporate various exotic non-Gaussian models. Okay, so this gives us a catalog of the dark matter in the universe. So I've plotted that here, and then we can look at what this looks like with Gaussian initial conditions and when we have pings. So what we see particularly visible at higher redshifts in this very long light cone box is you have structures forming at a characteristic scale in the halo catalog. You have more halos forming at a particular scale. Okay, and then we can do statistics on this. So if we make halo mass functions here, I've averaged 32 different halo mass functions to eliminate some of the statistical fluctuations. And then we do a relative entropy analysis, which is just a typical model we do where we take the halo catalog, divide the non-Gaussian halo catalog by the Gaussian, take the logarithm of that. So that's what we have on the right here. And so we can see the effect of the pings is essentially have a suppression of halos at small masses and then an increase at large masses. And this is where we've normalized the Gaussian part. So if we normalize the non-Gaussian part, that suppression at low masses kind of goes away and the high mass amplification stays. So we can see this in the relative entropy. Gaussian slightly over-predicts small mass halos and under-predicts low mass halos. Okay, so then from the Peak Patch halo catalogs, we use the WebSky simulations to generate mock observables of the sky. So looking through those many halos, we integrate along the line of sight, and then we have response functions for how a dark matter halo with galaxy cluster in it, or a single galaxy, depending on the size of the halo, how that will translate to various signals like thermal Sunyaev-Zel'dovich effect, lensing convergence, CIB, all sorts of different things we can look at. And so again, if we look at Gaussian conditions and ping, we get these structures of a characteristic scale here forming, same as we saw in the halo catalogs. Again, this is the CIB instead. So we have structures forming at a characteristic scale in these CIB maps. So here there's nothing, here there's more structure. Okay, so then we can use these to constrain our inflation models. So because these maps are statistically identical to actual observations, we can compare them statistically to those observations. So here I've got an example of a TSZ power spectrum on the left for the Gaussian WebSky simulations being compared to Planck, and we see there's a pretty strong agreement there. And then on the right, there's a comparison between a Gaussian WebSky and a non-Gaussian WebSky. This was for a much larger multipole range. This was just something we were doing. But the point is you can take Gaussian and non-Gaussian WebSky results and compare them directly to data like this. Okay, and so that's what I've done here. So here I'm gradually stepping up the amplitude of the non-Gaussianity. And so we see this clustering happening at a particular scale in the sky. So we can make these full sky maps, which are analogous to something you would get out of, say, Planck, measuring the TSZ sky. And then we can compare these directly with Planck data. So in the bottom left, I've shown a power spectrum where we're gradually stepping up the amplitude of the ping non-Gaussianity. And we can see you can actually constrain the model parameters of your primordial non-Gaussianity based on how well they agree with Planck data. Okay. And yeah, so again, we can see the non-Gaussian effects in the CIB. This is a fly-through of a very deep redshift box made by my colleague Dongwoo Chung for CIB work we're doing, or line intensity work we're doing, pardon me. And so again, we can see we have so many different templates where this effect is visible. And so we can use all kinds of different experimental data to constrain these inflation models. And again, we can come back to that relative entropy approach, and we actually see the same effect in the relative entropy of the line intensity map as the halo catalog. So we see the same suppression of halos at the low masses and amplification at high masses. So yeah, we have this wealth of statistical data we can use. So yeah, I just want to plug the work I'm doing with my colleagues. We're currently working on a new WebSky 2.0. This is going to have relativistic corrections to the TSZ. It's going to have an overhaul of the spectral energy distributions in the CIB, post-Born approximation to lensing convergence maps, and then optimizations to the largest optimizations to the computer architecture so we can get the biggest halo catalogs possible. And so the point is we're making mocks that will be for next-gen surveys that have extremely high resolution. So here, Dongwoo Chung has put together what those observations would look like, comparing them to actual data. So we have some videos here with chord and CCAP prime and COMAP, different beams. So yeah, that's what I want to talk about today. I just wanted to show that we can actually use this large scale structure to constrain inflation models that are otherwise unconstrained or poorly constrained by the bispectrum. So thank you very much. And if you have any questions, please let me know.